Good morning, students. Welcome to physics class. Now, as we have introduced the concept of electric potential energy, now today we will discuss few numerical on the concept of potential energy. So after that, you will be able to solve the numericals by yourself. So let's start with the first numerical. As in the statement, it has been given, if one of the two electrons of hydrogen molecule is removed, we get a hydrogen molecular ion H2 plus. In the ground state of hydrogen ion, the two protons are separated by a distance of 1.5 angstrom and electron is roughly 1.1 angstrom from each proton. Determine potential energy of the system. Statement, this is NCERT question I am taking here. As one of the two electron of hydrogen molecule we have taken is removed, we get a molecular ion H2 plus. Now see as we have taken this hydrogen molecule we are taking and one of the two electron is removed, so here it will be two protons and one electron. Let it be Q1, it be Q2 and it be Q3. These are protons. As per the statement, the separation between them is 1.5 angstrom. And the distance between this Q1 and Q2, that is electron and proton, is 1 angstrom. Same is here. Let this be R1, this you can take it as R2 and this as R3. So now, what you have to find here? Determine potential energy of the system. So, you have nothing to do, simply apply the formula for potential energy. As potential energy is K, system consisting of three charges, K Q1 Q2 by R1. As per the formula, K is common, so I am taking it outside the bracket. For Q1, Q2, this is K Q1 Q2 by R1. Similarly, for second system of charges and third system of charges, this will be plus K Q2 Q3 upon R2. This is R2 distance among Q2 and Q3. Similarly, Q3 Q1 for these two charges and the separation distance is R3. Now what you have to do, simply substitute the value, just you have to solve it, nothing else. It's a simple numerical. So we will take the value of K. First of all, we will substitute value of all the charges. Q1 is minus Q, Q2 is plus Q, distance is 1 angstrom, 10 raised to the power minus 10 meter. I can mention it here. 1 angstrom is 10 raised to the power minus 10 meter. So now second charge is Q2 is plus Q, Q3 is also plus Q, distance is 1.5, 10 raised to the power minus 10, plus Q3 into Q1, Q into minus Q by 10 raised to the power minus 10. Now U will be, now you can see in this result Q square can be taken outside the bracket and 10 raised to the power minus 10 can also be taken outside. So it is K Q square upon 10 raised to the power minus 10. Here it will be minus 1. Here it will be plus 1 upon 1.5. Here it will be minus 1. Now you can substitute the value of K. K is 9 into 10 raised to the power 9. Charge is 1.6, 10 raised to the power minus 19 square. This value is 10 raised to the power minus 10 and it will be, you can simply write it as 10 upon 15 minus 2. Now this is the calculation part. This when you will solve, you can do it by yourself, and I am just coming to the final conclusion point. This is homework for you because this is a calculation. You can simply cut and get the result. If you will solve it, whatever be the value will come, this will be in joule. But if you want to find the result in electron volt, then what you have to do, Divide this entire result by electronic charge value. This I have to tell you. If you want to stop up to joule, it's okay. No one can deduct mark for that unless and until it has been asked in the statement, find the answer in electron volt. So it is 2 by 3 minus 2. Now, as this has been divided here, now the answer will be in electron volt. So now, when you will solve all these steps, you will get the result to be minus 19.2 electron volt. You can try it at your home, that the value comes out to be this one. So this will be the total energy, that is the potential energy of the system. Now next numerical, that is 4 charges are arranged at the corners of a square ABCD of side D. ABCD of side D. Charges given here. Find the work required to put together this arrangement. What is the work required? What is energy required to put together all the charges at this vertices of a square? A charge Q0 is brought to center of square. 4 charges being held fixed at its corners. How much extra work is needed to do this? So first of all, you have to understand the statement, what is given in the statement, that is the prime factor. If you are familiar what is asked in the statement, then the half work of the numerical is done. See, as per the statement, as 4 charges are placed fixed at the corners, their charges and polarity has been mentioned in the figure. Now, first of all, you have to find total energy, total work required to put together this arrangement. It means, in simple terms, you have to find total potential energy of the system. In the second part, it has been given that by somehow, if Q0 is brought to center of the square and these charges at the corners being fixed, how much extra work is needed to do this? What will be the extra work done to do this? So now, as per the statement, first of all, you will find total work required to put together all the 4 charges. As the formula for potential energy is K, Q1, Q2 upon R. Being we have 4 charges, so there, what will be the interactions among combinations? 1 charges at AB. So here it will be K. K will be common among all these, so I will take it to be common. So before it, first of all, let me take it AB, BC, CD, DA. This is all equal to D side. Now AC, BD. By Pythagoras theorem, if you will find, this value comes out to be root 2D. And if you have to take distance from center, that is AO, BO, CO, DO. This will come out to be root 2 D upon 2, that is D upon root 2. This we have done so that we can now easily use it in the numericals. Now coming to the potential energy. As potential energy for each pair of charges. First of all, first pair of charges at A and B. So it will be K, Q1 plus Q, Q2 minus Q upon R, distance is D. For second pair of charges at B and C, so it will be K, again Q minus Q upon D. For third pair of charge at C and D, this will be K, Q minus Q upon D. And for fourth pair of charge at A and D, it will be K minus Q plus Q upon D. Apart from these 4 pair of charges, there are 2 more pair of charges along the diagonal. So for that, it is plus K, Q, charge at A and C, both are plus Q, and separation distance between them AC, this AC is root 2 D. Similarly, charges at B and D, this is plus K minus Q upon root 2 D. Now, as we see here, what are the common factor? We will take it outside the bracket K, Q square upon D. I am taking common from all these 6 pairs. From the first factor, it is minus 1. From the second factor again minus 1, third factor minus 1, fourth factor minus 1. From these two, as we are taking, this will be plus 1 by root 2. Again, here it minus minus plus, it will be plus 1 by root 2. Simply we have taken the factor common. Now, k q square upon d, rearranging this all 4 factor, this is minus 4 plus 2 upon root 2. So, if you are taking this work done, this comes out to be, you can, if you want, you can put the value of k, this is 1 by 4 pi epsilon naught q square upon d, and this is 2 by root 2. You can see this 2 by root 2, if you will rationalize it, this will be 2 root 2 upon 2. So directly you can replace it by root 2. So this is your minus 4 plus root 2. So this is the total potential energy, total work required to put together all the charges at their respective positions. Now in the second part, charge Q naught is brought to center. So how much extra work is needed to do this? So correspondingly, now extra work done will be equal to forward charge Q naught. Now this will be equal to potential at O due to all the charges present at the corners. So Q naught into potential at O due to charges at A, B, C, D. So again it will be K. This is your charge at A is plus Q, KQ upon AO. Charge at B, this is minus KQ upon BO. Charge at C, this is plus Q, so KQ upon CO, or OC you can write, plus K into minus Q, charge at D upon DO. Now AO, BO, CO, DO all having the value, this is your D by root 2, and here Q and K are common, let me take it outside, K, Q, Q naught, and let me put the value, this is let me take this AO, BO, CO, DO, which is value D by root 2, let me take it as D dash, because value is common, so to make the calculation simple you can do, or you can put the value also, this will be 1 by D dash minus 1 by D dash plus 1 by D dash, this minus 1 by D dash. So it is K, Q, Q naught upon D dash, this is 1 minus 1 plus 1 minus 1. This will cancel out, result is 0. You can take this D dash as D by root 2, it depends upon you. I want to calculation to be simple, that's why I have represented it by other symbol. So this extra, though no work is done in putting the charge at this point, keeping other charges to be fixed at the position. See, the numerical is simple one. Here basically first of all we have to just calculate the total work done, and then what we have to do, when as the charge Q naught to be fixed at the position, other charges be fixed, as Q naught is brought from certain means, then what will be the extra work done? Now as extra work done will be Q naught into potential at the center due to all the other charges being fixed, as no change will be in the distance, so no work will be done. I hope this is an NCERT solved question. So just you will practice such kind of numericals more from the books. Now next numerical. 3-point charges of 1 coulomb, 2 coulomb, 3 coulomb are placed at the corners of an equilateral triangle of side 100 centimeter. Find the work done to move these charges to the corner of a similar equilateral triangle of side 50 centimeter. Within the same triangle, you have to move the charges at the corners of another equilateral triangle with less side, almost half. So how to start this question? See, this is an equilateral triangle whose sides are equal. Let it be R1 each, and charges are placed having different magnitude. That is, Q1 is 1 coulomb, Q2 is 2 coulomb, Q3 is 3 coulomb. These are placed at the corners of an equilateral triangle having side. That side distance is given to be R1 is 100 centimeter, that is 1 meter. Now, first of all, you have to find that what is asked in the statement. Find the work done to move these charges to a corner of a similar equilateral triangle. Obviously, when we have taken that the charges are moved to the corners of another triangle whose side is R2, and this R2 is given to be 50 centimeter, that is 0.5 meter. So first of all, you have to find work done for the charges to be at this position. Then you have to find work done to be situated, charges to be situated at another triangle, inner triangle of 50 centimeter side. Then what work has to be done? Then you have to take difference between the work done. That means final potential energy minus initial potential energy. So first of all, initial potential energy when the charges are situated at the side of at the corners of a triangle of side 100 centimeter. So first formula, let me take K Q1 Q2 by R1 plus Q2 Q3 by R1 plus Q3 Q1 by R1. K value is 9 into 10 to the power 9 and R1 is common. We will substitute value later on. Charge first is 1 coulomb, second is 2 coulomb, second is 2, third is 3. Third is 3, first is 1. 9 into 10 to the power 9 and R1 is 1 meter. So it is 2 plus 6 plus 3. See here, no new concept is done. Just we have to learn the formula. This is the formula which you have to learn for number of charges. So here we have substituted the values. Now on solving, it will come out to be, this will be 99 10 to the power 9 joule. This is the initial potential energy. Now, as the charges has to shift to the corners of a triangle of smaller side. Now, as the charges to be moved to side of a triangle, corner of a triangle, so new potential energy, final potential energy will be again K Q1 Q2 by, distance is changing, R2. Rest all factors will be same, Q2 Q3 by R2 plus Q3 Q1 by R2. So K upon R2, Q1 is 1, Q2 is 2, Q3 is 3. So putting the values, then this substituting the value of K and R2 as 0.5. This is 2 plus, this is 6 plus 3. Now here it is, you can just take it as 9 into 10 to the power 10, 5 into 10, this decimal we have taken here, and here it is 11. Then it is, can you write it as 2 into 99 into 10 to the power 9 joule? This is the step. We can multiply it also, but for the simplification of calculations I am leaving it as such. See, here it is 99 into 10 to the power 9. Here it is 2 into 99 into 10 to the power 9 joule. We can multiply it. Now you have to find work done to move the charge. It means what you have to do, work done will be equal to final work done minus initial work done. So it will be 2 into 99 into 10 to the power 9 minus 99 into 10 to the power 9. That is comes out to be this one. So this is your calculation, how to proceed. Basic concept here to understand is that when you are solving this numerical, first of all, as the charges are situated at one particular point, you have to calculate potential energy for such 3 charges. And then charges being shifted to new position, so here you will calculate the new potential energy. Now the difference of these two will give you the total work required to be done so that charges to be shifted from one triangle corner to another triangle. This is all in this numerical. Now one more numerical. Here, this is also NCERT solved question. Determine electrostatic potential energy of a system consisting of two charges, 7 microcoulomb and -2 microcoulomb with no external field at -9 centimeter 0, and 9 centimeter 0 respectively. Let me understand this part first. See here, electrostatic potential energy you have to find between the two charges that are of 7 microcoulomb and -2 microcoulomb. These are situated at points. Where are the points? -9 centimeter. This -9 centimeter 0 coordinate means, see what you understand by this. This is x coordinate exists, yz coordinate is not existing. It is along positive x-axis, it is along negative x-axis. So separation distance between, if this is origin, so separation distance D will be 18 centimeter or 18 into 10 to the power -2 meter. Two charges are situated at these two opposite corners, equal distance from the origin. This is the meaning of the statement. See, again let me recall. Determine potential energy of system consisting of two charges, 7 microcoulomb -2 microcoulomb with no external field. No external field was present there at these 2 points respectively. Now, how much work is required to separate the two charges infinitely away from each other? How much work is required to separate the two charges? Basically, work required to separate to them to an infinite distance away from each other. First of all, you will find the potential energy corresponding to this distance, and when you have to separate it at infinite distance, potential energy will be 0. So from these two steps, what we conclude? First of all, you will apply the formula for potential energy, that is K Q1 Q2 by R, and when you have to take it at infinity, potential energy will be 0. So let me take these two steps first. Now, so in the first step, as the charges are separated by this distance, so potential energy will be K Q1 Q2 by R, and this is 9 into 10 raised to the power 9, Q1 7 into 10 raised to the power -6 because it is in microcoulomb, -2 into 10 raised to the power -6. Separation distance is 18 into 10 raised to the power -2. So when you will solve it, then this is cancelled. Then what you will get? 7 into 10 raised to the power 9. This is -6. This is negative sign will come, and this is -6, and this is your +2. This -2 comes in the numerator. -7 10 raised to the power 11 -12. This is -7 10 raised to the power -1. So it is -0.7 joule. So this is the initial potential energy. In the first part is to as asked, you can check your statement. Determine electrostatic potential energy of system consisting of two charges. So we have calculated potential energy. This is your first A part. Now in the B part, how much work is required to separate the charges? It means we have to separate the charges at infinite distance apart. When R is infinity, potential energy will be 0. Let it be U2 and it be U1. So work required will be U2 minus U1, potential energy, final minus initial. So it will be 0 minus initial, it is -0.7. So it will be 0.7 joule. This is the B part. Here, how much work is required to separate the two charges at infinite distance apart. So in the first and second part, we have calculated the values. Now just be careful while understanding C part. Suppose that the same system of charges is now placed in an external electric field. This is given to be A upon R square, where A is any constant that is having value 9 into 10 raised to the power 5 coulomb per meter square. We don't know anything about it, just value has been given. What would the electrostatic energy of the configuration be? Now, if you will recall that we have done potential energy of system of charges maybe 2, 3 and without external field. And we have taken one last case in which some external electric field was also taken. So that will also contribute. Here that concept will be utilized. So let's see. Now, in external electric field, total potential energy will be, first of all, initial due to the presence of charges separated by a certain distance, plus first charge as some field is present. So due to that, some potential will be up to distance R1. For Q2 charge, potential energy will be there. That is some potential is present due to that external field, and hence Q2 charge is placed in it. So this will be the total potential energy when the system is placed in some external field. Now this is a formula. Now, as in the statement, only one thing is given, that is E is equal to A upon R square. No information about the potential. So think, what should we do further? As we know that E is equal to minus potential gradient, and from here we have also taken the formula minus E into dr. Yes, now we will apply here. You have to apply this also here. So now put the value. V is equal to minus E will be A upon R square dr. So here it will be minus A R raised to the power minus 2 dr. Here it is minus A integrate x raised to the power n plus 1 in the integration, x raised to the power minus 2, this is r raised to the power minus 2 plus 1 upon minus 1. So what you will get, this will be A, this is minus 1 and this is again minus 1 by r, which will be A upon r. So potential here is A upon r. Potential we have taken. Now for R1 and R2 you will use the suffix. Now just all the points are clear now. You have to put the values. So total potential energy K Q1 Q2 by R, that is you have taken from this point. You will use it as such. So this will be minus 0.7 plus first charge having magnitude 7 into 10 raised to the power minus 6 and potential, that is A upon R1 plus second charge minus 2 into 10 raised to the power minus 6 into A upon R2. See, in the statement value of A is given. Now what will be the value of R1 and R2? Coming to the figure, here this distance, one of the distance will be R1 and this distance will be R2. So numerically this distance magnitude is 9 centimeter here, 9 centimeter here. So this R1 and R2 will be 9 centimeter, that we will convert in meters. So here it will be minus 0.7 plus 7 into 10 raised to the power minus 6. Value of A is given in the statement 9 into 10 raised to the power 5 coulomb per meter square. R1 is 9 into 10 raised to the power minus 2. Then minus 2 10 raised to the power minus 6. Again substituting A to be 9 into 10 raised to the power 5 and distance, that will be, this is not R square, this is R2. Here it is 9 into 10 raised to the power minus 2. Now all the values are here and when you will solve it, it will come out to be minus 0.7. This will be plus 70. When you will solve all this by solving, it will be plus 70. This will cancel out, this will cancel out. Now you have to rearrange the values, and the third term it will come out to be minus 20. So here the answer will come out to be, this will be 49.3 joule. Check your answer. So this is all. This is the statement. Let we have just review of the statement. As per the statement, we have to calculate potential energy for system of these two charges. So what you have to learn? Formula K Q1 Q2 upon R. R should be in meter. Why? Why should be in meter? Because K, it is in SI system. The value 9 into 10 raised to the power 9 along with unit, it is in SI system. So that's why we have taken the distance in meter instead of centimeter. Calculating the value of potential energy minus 0.7 joule. Now when you have to separate them at infinite distance, the R will be infinity, final energy will be 0. So net work done, that will be final energy minus initial energy, so it will come out to be 0.7 joule. Very important, that is the third part. When there is a concept of external field, potential energy will be K Q1 Q2 upon R plus field due to the external field present. So Q1 is placed in that external field, so potential will contribute there. Similarly, Q2 is also placed in the same field multiplied by potential. Now here the concept of potential is required, but we have given only electric field. So we will use the concept of potential gradient to calculate the value of electric potential. From here you will integrate it and you will calculate potential to be A upon R. Now all the unknown parameters are known to us. Now here you will put the value in potential energy expression in external field. When you will substitute these values, the answer will come out to be 49.3 joule. So this is all. I find it difficult for you people to understand, but if you will just repeatedly watch this video again and again where you are facing problem, then you will be able to understand it. And if you feel any doubt, you can call me. So this is all for today, as we have done 4 numericals on electrostatic potential energy. Now revise these concepts, because after this, in the next lecture, I will give you, in the next instead of next topic, I will give you assignment that will be as a test for you people, and that can be the questions on the basis of potential and potential energy. So first of all, I advise you to prepare questions of electric potential and potential energy. These are all numerical problems can be there. So just do the work. Now I am just completing it. Thank you. Have a nice day.